It is understandable to feel frustrated about the situation, but it is important to learn from the experience to avoid similar mistakes in the future. Here are some key points to consider. Firstly, readiness. Before starting a project, ensure that all the necessary preparation and planning have been completed, including obtaining permits and approvals from relevant authorities. In this case, it might have been beneficial to double-check the plans and verify the adequacy of the installed conduit before proceeding with the installation. Secondly, compliance with code. As an electrician, it is essential to be familiar with the electrical codes and standards that govern your work. In this instance, being aware of National Electrical Code Article 230.90 would have prevented the improper installation of the meter main. Thirdly, seeking clarification. When in doubt, do not hesitate to consult with more experienced colleagues, supervisors, or industry experts to clarify technical issues. It is better to ask questions and ensure proper guidance than to risk making costly mistakes. Fourthly, thorough inspections. Encourage thorough inspections of your work, both by yourself and qualified inspectors. This helps identify errors early on and allows for timely corrections. Fifthly, documentation. Keep accurate records of the project, including plans, design changes, and inspection results. This documentation can be valuable for future reference and troubleshooting. Remember, it is natural to encounter challenges and make mistakes during the course of a project. The important thing is to learn from them, improve your knowledge, and strive for excellence in your work. Now diving into National Electrical Code Article 230.90, this section addresses the overcurrent protection requirements for service conductors. It is crucial for ensuring the safety and proper functioning of electrical systems. This section mandates that service conductors must have overcurrent protection at the point where they receive their supply. The overcurrent protection device, such as a circuit breaker or fuse, should be sized and installed to protect the service conductors from overloads and short circuits. The rating of the overcurrent device should not exceed the ampacity of the service conductors it protects, except as permitted in specific situations outlined in the code. There are some exceptions and specific requirements outlined in 230.90 that allow for adjustments to the overcurrent protection based on factors such as the type of service, the connected load, and the characteristics of the equipment being served. For example, 230.90 typically covers the protection of service conductors for dwelling units. This section allows the overcurrent device to be sized based on the calculated load, but it also sets limits on the maximum size of the overcurrent device. 230.90b typically covers the protection of service conductors for other than dwelling units. This section outlines different requirements for overcurrent protection based on the specific application. It's important to note that the requirements in 230.90 are intended to protect the service conductors themselves and not necessarily the downstream circuits or equipment. The overcurrent protection for those circuits and equipment is covered in other sections of the National Electrical Code. In the original scenario, the intention to install a 100 amp meter main with 60 amp conductors highlights a direct violation of 230.90. The 100 amp overcurrent protection in the meter main would not adequately protect the 60 amp conductors from overcurrents, potentially leading to overheating and fire hazards. The conductors are sized for the load, but National Electrical Code 230.90 prioritizes protecting the conductors themselves, not just the load. Even though the load might not exceed 60 amps, a fault could cause a much higher current to flow, which the 100 amp breaker would not trip on quickly enough to protect the 60 amp conductors. The fact that the installation passed inspection does not absolve the electrician of responsibility. Inspectors can miss things, and ultimately, the electrician is responsible for ensuring that the installation meets all applicable code requirements. It is important to always double-check one's work and be familiar with the relevant code sections. Here's a more detailed breakdown of the key concepts and considerations related to National Electrical Code 230.90. Firstly, the purpose of overcurrent protection is to protect conductors and equipment from excessive current flow, which can cause overheating, insulation damage, and fire hazards. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a predetermined level. Secondly, ampacity is the current carrying capacity of a conductor expressed in amps. The ampacity of a conductor is determined by factors such as its size, material, insulation type, and installation conditions. The National Electrical Code provides tables and guidelines for determining the ampacity of conductors under various conditions. Thirdly, service conductors are the conductors that run from the serving utilities equipment to the service disconnecting means in a building or structure. Service conductors are typically larger in size than branch circuit conductors because they carry the entire load for the building or structure. Fourthly, the service disconnecting means is the main switch or circuit breaker that disconnects the entire electrical service from the building or structure. The service disconnecting means is typically located near the point where the service conductors enter the building or structure. Fifthly, National Electrical Code 230.90 requires that service conductors be protected against overcurrent at the point where they receive their supply. This means that the overcurrent protection device must be located at the supply end of the service conductors, typically at the service disconnecting means. Sixthly, the rating of the overcurrent protection device must not exceed the ampacity of the service conductors it protects. This ensures that the overcurrent device will trip or blow before the service conductors are overloaded. Seventhly, there are some exceptions to the general rule that the overcurrent protection device must not exceed the ampacity of the service conductors. For example, National Electrical Code 230.90 allows the overcurrent device to be sized based on the calculated load for dwelling units. Eighthly, the overcurrent protection requirements in National Electrical Code 230.90 are intended to protect the service conductors themselves, and not necessarily the downstream circuits or equipment. The overcurrent protection for those circuits and equipment is covered in other sections of the National Electrical Code. Here are some practical examples to illustrate the application of National Electrical Code 230.90. Firstly, a single-family dwelling has a calculated load of 100 amps. The service conductors are sized to carry 100 amps. According to National Electrical Code 230.90a, the overcurrent protection device can be sized up to 125 amps as long as the calculated load is not exceeded. Secondly, a commercial building has a calculated load of 200 amps. The service conductors are sized to carry 200 amps. According to National Electrical Code 230.90b, the overcurrent protection device must not exceed 200 amps. Thirdly, an industrial facility has a calculated load of 400 amps. The service conductors are sized to carry 400 amps. According to National Electrical Code 230.90b, the overcurrent protection device must not exceed 400 amps. However, the facility also has a large motor that requires a separate overcurrent protection device. The motor's overcurrent protection device can be sized larger than the ampacity of the motor conductors, as long as it does not exceed the maximum size allowed by the National Electrical Code. Here are some common mistakes to avoid when applying National Electrical Code 230.90. Firstly, oversizing the overcurrent protection device. This is a common mistake that can lead to overheating and fire hazards. The overcurrent protection device must be sized to protect the service conductors, not the load. Secondly, using the wrong type of overcurrent protection device. There are different types of overcurrent protection devices, such as circuit breakers and fuses, each with its own characteristics and applications. It is important to use the correct type of overcurrent protection device for the specific application. Thirdly, failing to properly install the overcurrent protection device. The overcurrent protection device must be installed in a location that is readily accessible and protected from damage. It must also be properly connected to the service conductors. Fourthly, neglecting to label the overcurrent protection device. The overcurrent protection device must be labeled with its rating and the circuit it protects. This helps to ensure that the correct overcurrent protection device is used for the specific circuit. Here are some additional considerations for applying National Electrical Code 230.90. Firstly, coordination with other overcurrent protection devices. The overcurrent protection devices in an electrical system must be coordinated to ensure that the overcurrent device closest to the fault will trip first, minimizing the extent of the outage. Secondly, selective coordination. Selective coordination is a design approach that ensures that only the overcurrent device closest to the fault will trip, even under high fault current conditions. This is important for critical facilities such as hospitals and data centers, where a prolonged outage can have serious consequences. Thirdly, arc flash hazard. Arc flash is a dangerous electrical phenomenon that can occur when a fault current flows through the air. Arc flash can cause severe burns, injuries, and even death. It is important to take steps to mitigate the arc flash hazard when working on or near electrical equipment. Fourthly, National Electrical Code 110.16 requires that electrical equipment be marked with a warning label if it is likely to be energized while being examined, adjusted, serviced, or maintained. The warning label must include information about the arc flash hazard and the personal protective equipment required to work safely on the equipment. Understanding and applying National Electrical Code 230.90 is essential for ensuring the safety and proper functioning of electrical systems. By following the code requirements and avoiding common mistakes, electricians can help to prevent overloads, short circuits, and other electrical hazards. Always consult the latest edition of the National Electrical Code and seek guidance from qualified professionals when in doubt. Now consider the specific situation described earlier with the 1-inch conduit and the decision to use 4-3 underground rated direct burial conductors. While this might seem like a practical solution to fit conductors within the limited conduit space, it's essential to verify that this installation meets all applicable code requirements and safety standards. Firstly, conduit fill. The National Electrical Code specifies the maximum percentage of conduit fill allowed for different types of conductors and conduit sizes. This is to ensure that conductors can be easily installed and removed, and that heat can dissipate properly. Using 4-3 underground rated direct burial conductors in a 1-inch conduit might exceed the maximum allowable conduit fill, depending on the specific type of conductors and conduit used. It's crucial to consult the appropriate tables in the National Electrical Code to determine the maximum number and size of conductors that can be installed in a 1-inch conduit. Secondly, diode factors. When multiple conductors are installed in a conduit, the ampacity of each conductor must be derated to account for the heat generated by the other conductors. The derating factors are specified in the National Electrical Code and depend on the number of conductors in the conduit and the ambient temperature. Using 4-3 underground rated direct burial conductors in a 1-inch conduit might require significant derating of the conductor ampacity, which could reduce the overall capacity of the service. Thirdly, conductor type. Underground rated direct burial conductors are designed for direct burial in the earth and have specific insulation and jacketing requirements. While they can be used in conduit, it's essential to ensure that the conductors are suitable for the specific conduit type and installation conditions. The National Electrical Code specifies the types of conductors that can be used in different types of conduit. Fourthly, connections and terminations. The connections and terminations of the 4-3 underground rated direct burial conductors must be properly made and insulated to ensure a safe and reliable connection. The National Electrical Code specifies the requirements for connections and terminations, including the use of approved connectors and methods. In the scenario described, it's crucial to carefully evaluate the conduit fill, derating factors, conductor type, and connections to ensure that the installation meets all applicable code requirements and safety standards. If the installation does not meet the code requirements, it might be necessary to use larger conduit, different conductors, or other methods to provide a safe and reliable service. It's always best to consult with a qualified electrician or electrical engineer to determine the best approach for a specific installation. Now let's think about the fact the initial plan called for a 100 amp service to the garage, but because of the existing 1-inch conduit, the solution was to install 60 amp conductors. This raises a couple of key considerations. Firstly, load calculation. A proper load calculation should be performed to determine the actual electrical demand of the garage. This calculation should take into account all the electrical loads that will be connected to the service, such as lighting, receptacles, appliances, and any other equipment. The load calculation will help to determine the minimum size of the service conductors and overcurrent protection device required to safely and reliably serve the garage. Secondly, future expansion. It's important to consider any potential future expansion of the electrical load in the garage. If there is a possibility that the electrical demand will increase in the future, it might be wise to install a larger service than is currently required to avoid having to upgrade the service later on. Thirdly, conductor ampacity. The ampacity of the 60 amp conductors must be sufficient to carry the calculated load of the garage. The ampacity of a conductor is determined by its size, material, insulation type, and installation conditions. The National Electrical Code provides tables and guidelines for determining the ampacity of conductors under various conditions. Fourthly, voltage drop. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction and can reduce the efficiency of the electrical system. The National Electrical Code recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. When sizing the service conductors for the garage, it's important to consider the voltage drop to ensure that the voltage at the garage is within acceptable limits. Fifthly, overcurrent protection. The overcurrent protection device for the garage service must be sized to protect the conductors from overloads and short circuits. The rating of the overcurrent protection device must not exceed the ampacity of the conductors it protects. In the scenario described, the decision to install 60 amp conductors raises questions about whether the existing 1-inch conduit is adequate for the intended load and whether the conductors are properly protected. It's essential to carefully evaluate these factors to ensure that the installation meets all applicable code requirements and safety standards. It's always best to consult with a qualified electrician or electrical engineer to determine the best approach for a specific installation. And always remember that electrical work can be dangerous, and it's important to take all necessary precautions to protect yourself and others from harm. This includes wearing appropriate personal protective equipment, such as gloves, safety glasses, and insulated tools. It also includes following safe work practices, such as de-energizing circuits before working on them and testing circuits to ensure that they are de-energized. If you are not comfortable working on electrical equipment, it's best to hire a qualified electrician to do the work for you.